Good afternoon, everyone. Thank you for joining us in this webinar to know a bit more about the work that the Center of Power and Energy from INESC TEC and our partners have been developing. So today, the webinar is focused on stationary energy storage technologies and its applications for future distributed energy systems. So as you know, energy storage is key for the future decarbonization of the energy system, and particularly for the operation of the future power systems to deal with the increase and large-scale integration of renewable energy sources. And so today, the session will refer in the first place about the technologies for stationary energy storage, where we will look for the different technologies and most importantly, for the innovative technologies that are being developed by the group that Tiago Lagarteira represents today. And then Ricardo, that is a researcher from the Center of Power and Energy, will present a bit more the work that we have been developing for the management of energy storage in distributed energy systems, such as the microgrids, such as hybrid power plants, and also energy communities. So first we will start with Tiago. Tiago is a project engineer at the Laboratory for Process Engineering, Environment, Biotechnology and Energy from the Faculty of Engineering of University of Porto. He is an MSc in Chemical Engineering, and he has been working mainly in the development of electrochemical energy storage technologies. And his presentation will be about these innovative technologies that its group has been developing, the challenges, the characteristics and the opportunities that this will also bring to the management of future power systems. So the session, we will have this first presentation, we will have a short period for questions to Tiago, and then Ricardo will follow. Also, we'll finalize with the question period. You can use the Q&A to ask the questions, and then I will read them and let the presenters today to answer you. So I will pass to Tiago. Tiago, thank you for accepting the invitation.
And thank you for the introduction. So I think I can share my screen now. Okay, so Clara, can you confirm that you see my screen?
Yes. Okay.
So good afternoon, everyone. First of all, it's a pleasure to deliver here or to present some of the most interesting activities that we do on our group at this webinar. So my talk today, like Clara already introduced, is a little bit related, of course, to this paradigm of the energy transition, and to showcase a little bit what we do that is somehow unique or different from also other academic groups in the field of efficient energy storage and conversion. And I will mainly address, we do also research on other types of energy storage technologies, not related to electrochemistry or photoelectrochemistry, but of course, considering the topic of this session, I will talk mainly about electrochemical systems and a little bit about photoelectrochemical systems, but of course, they share many similarities, as you will see in the course of this presentation. So just a quick introduction about our research group. So we are based in the Faculty of Engineering, the University of Porto, in the north of Portugal. So this is a top view of our university. We are based here, the Chemical Engineering department. And inside this department, we have slightly independent groups, and we belong to the largest group in the Chemical Engineering department, headed by Professor Adélio Mendes. So this is already an old picture of our group. Now we are more, and some of the faces here are not with us anymore, and we have new faces. But okay, just a quick introduction to this topic. The problematic of the energy transition. I think that among all of us, we are aware of the urgency that our humanity is facing in the times that we have now. And on the left side, I have here a chart that I enjoy to make this introduction, which is a study published on Nature, where the scientists here, they estimated a budget of CO2 left to emit before we surpass the limits set in the Paris Agreement. So in conclusion, they conclude that we have 600 gigatons of CO2 left to emit before we dangerous overcome the 1.5 to 2 degrees C in the average temperature of the planet. So what this means is that not to approach the maximum plafond that we still have, we need to start decarbonizing the energy sector as soon as possible. But the main differences about these lines is that the sooner we start decarbonizing, the smoother this transition can be. And this is very important because the decarbonization is not only important to be feasible in terms of environmentally, but also economically, but also socially. And the more that we delay this transition and stop CO2 emissions, more abrupt this transition needs to be. And this will have a big impact mainly on the final price of energy. And we are already facing this not due to the normal standard of the transition as we were expecting, but from other external and geopolitical issues. But yes, this uncertainty already is luckily putting more people aware of the urgency that we need to make this transition. But if we need to do an on-off transition, this will make the energy become more expensive, raising social problems, and not having all the people engaged, mainly those who are not from the field and who are not aware of the problematic of a smooth, but also it needs to be swifter, this transition. So in the right side, I have here, okay, the share of renewable sources in the electricity market in the different countries in the European Union. We can see that luckily Portugal is in 4th place. So we are among the countries that have the highest share of renewable electricity today. Unfortunately, the European Union, the average is less than 50%, and we still have some countries that are very delayed in this adoption on renewable energy. So then, regarding renewable sources, because despite the discussion between nuclear and also renewable energy sources, the strategy from Europe is mainly based on implementing and making massive investments on renewables. We see here in this chart that renewables, of course, they are known to be not only seasonal, but also intermittent. For example, in the case of Portugal, we have great potential to have photovoltaic energy to become very, very competitive. However, as you can see here in this axis, we have months of the year. So this means that we can extract more from our infrastructures during the summer. And also very important is that with sunlight, we produce electricity during the day. But in our houses, we need the energy during the night. And if we do not, of course, if we do not immediately use the electricity that we are producing from photovoltaics, it is simply disregarded. So energy storage is a need. And the problem with the electrical grids is that they do not go very well with peaks and lack of energy. So they need to be steadily balanced. And in this case, to provide a stable electricity grid or to stabilize it, we need different storage solutions, not only in terms of response time, but also in terms of power and energy density. So this is a little bit what I introduced here. So in terms of electrochemical energy storage, we have different types of solutions, from capacitors to supercapacitors, batteries, and here we have fuel cells, but I would say this is more hydrogen. And of course, these different technologies, they have different specific power and also specific energy. So energy, of course, is more related to the capacity. Power is responsible to, per unit of time, how much energy we can deliver. So we can see that capacitors have a very high specific power, and hydrogen has the lowest in this case. But in terms of capacity, hydrogen has the highest value, followed by batteries, supercaps, and then capacitors. Also very important, depending on the application that we need these storage systems, is the notion of the density, the energy density and power density, but also related to gravimetry. So per unit of mass. In this case, we had per unit of volume. This is quite relevant, mostly in the fields of mobile application and also transportation, because here the space needed for these systems, it's much more limited. So we need to provide compact systems with relevant energy density and also power density. And again, in a gravimetric point of view, hydrogen is the highest, has the highest capacity, followed by batteries. But if we talk about power density, in this case, hydrogen has the lowest compared to capacitors, supercapacitors, and also batteries. So the main outcome of this chart is that the ideal energy storage system will depend mainly on the application. And since we have different application with different needs, a mix of solutions is needed. So this is not about competing between electrochemical energy storage systems, but competing again the use of fossil fuels. So in this case, we will definitely need a mix of solutions that will be more advantaged depending on the application. So now specifying a little bit the energy storage systems related to batteries. In this case, we have again a relationship between energy density and also specific energy, so capacity. And I would like to present you here the all vanadium flow batteries, in this case with very low energy density and also capacity. And we have here lithium ion. So lithium ion is the most known battery technology that is being used mainly in mobile applications, but also in lightweight vehicles. But we also have some interesting batteries, some based on lithium and some other ones, Redoxel batteries that are much more disruptive approach but less mature at lower TRL, but that will deliver higher capacities and also higher power densities when compared to lithium ion. So just for your reference, gasoline stays here. So this is a little bit our reference in terms of needs or what we need to deliver with a completely different propulsion system. So regarding redox flow batteries, so redox flow batteries are a technology that is already in the literature since the 50s. They experienced a very slow pace of development. NASA was the first one developing these at the small stack level, but then most of the work was done by the group of Skilas Kazakos. So Skilas Kazakos is a professor. She is based in Australia. She is not so active today anymore, but her group were the main pusher on vanadium redox flow batteries. Then in 2011, considering the awareness of the population towards electrification and decarbonization, the research interest on redox flow batteries started increasing. And today we have 9 different types of redox flow batteries that are already in the market. Okay, not very large scales, but they are already, and you can already see them on the market. However, why redox flow batteries are so interesting? Regardless of the low densities in terms of capacity and also power, in this battery, the power is decoupled from capacity. So here you have a small sketch of a single cell of a redox flow battery. And you can see here that the energy, unlike lithium-ion batteries, is not, let's say, confined to a solid-state electrode in this case, but the energy is instead in an electrolyte. We call it an electrolyte. So what happens here is that we have the hardware, so the components of the cell, end plates, porous transport layers, and also a membrane that electrically insulates both electrodes and only allows the passage of ions. But the energy itself, electricity, is stored in liquid electrolytes that we can flow inside the battery and that we can charge or discharge it depending on the operation mode by using very simple devices like pumps. Here we have a sketch of the components. This is okay, the membrane inside. All the other components are gaskets to avoid leakages. And we have here these black ones. These are where the charge transfer takes place. So these are the electrodes, typically carbon felts. Then we have current collectors, graphite plates to be able to circulate the flow and to have a more homogeneous distribution, and also the end plates where we tight the screws to provide compression. Of course, in an industrial device, what you have is a stack of these cells, so we can stack them in series connection. And yes, so most of the components are very similar to what you see in single cell. We have the positive electrolyte working on the positive, circulating in the positive sides. We have ion exchange membranes, bipolar plates, and of course the end plates. In the case of the vanadium redox battery, in the positive side, we have a redox couple, which is based on vanadium 4 and vanadium 5. 4 and 5 are the oxidation states that vanadium has in this positive side. And in the negative electrode, we have redox reactions between vanadium 2 and vanadium 3. And of course, here we have the standard the standard potentials, considering the standard hydrogen electrode for each one of these reactions. And what we have when we have a discharge cell is that we have an OCV of 1.25 volts. So of course, to be able to charge it, we need to provide electric power. When we are in discharge mode, the system realizes work for us, so we are able to transform chemical energy again into electricity. So typically, just for some raw numbers, the vanadium molar concentration typically is about 1.5 molar. We need to acidify our aqueous solutions, and typically we do it with 2 molar of sulfuric acid. And the maximum current densities reported so far are in the range of 150 milliamps per square centimeter. Here, square centimeter, we are talking about geometric surface area of the electrode. So at our group, we have been intensively doing some R&D since 2015 on vanadium redox batteries. Our best performances were in the range of more than 80% cycle energy efficiency. We were able to work during long-term experiments at current densities of 100 milliamps per square centimeter at 1 volt. And in this case, we were able to upscale, starting from single cell, where we were developing components, to some small stacks. Here you can see a small 5-cell stack with 300 square centimeters of active area, that then we added more cells to this stack to reach 1 kilowatt. And in the right side, we have 2 5-cell stacks with 1250 square centimeters, 5 cells each stack, and they were connected in parallel, these 2 stacks. So this was a national project together with FASEC that ended just before the pandemic, so by the end of 2019. So some of the advantages of these batteries. Okay, they are very cheap to construct, low levelized cost of energy. They can enable high current densities, very high round trip efficiencies, and they are very stable. Additionally, also because we use aqueous-based electrolytes, they are safe and they are reliable. However, they raise some environmental concerns. So sulfuric acid and also vanadium aqueous solutions pose some environmental concerns. Also, the low solubility of vanadium at higher temperatures is a problem because it will decrease, of course, our power density of the system. And also, vanadium in general has a high price. It is not a critical material, but it is dissolved in very small concentrations on the sea. So this means very high OPEX to get vanadium. So that's why the cost of vanadium per kilowatt hour is excessive for the target set by the European Union for electricity storage. And they also have a low energy density, so around 25 watt-hour per liter. So in this case, I will mention some other technologies on redox flow batteries that are emerging. So a list of them: aqueous organic redox flow batteries, semi-solid flow batteries, solar redox flow batteries, solid mediated flow batteries, and also metal air. I will not go into all of them. I will only mention the ones that we are currently working on and that we think that they have more potential. So here, these aqueous organic redox flow batteries, they are quite interesting because as redox pairs, we use organic molecules. So these organic molecules are very inexpensive to synthesize. And briefly, we only use very abundant materials also to synthesize these. So they have very high potential in terms of cost for the system. And here, okay, we can see the round trip efficiency gets closer to 85%, also relevant current densities. But our interest on this type of batteries within our group is related to redox, solar redox flow batteries. So the solar redox flow batteries are a hot topic right now because we can include into one device the capture of sunlight to produce electricity, but in the same device, we are able to produce solar fuels without the need to have independent photovoltaic panels to then power electrochemical systems. So here we can integrate them into one device, and also we can do a very interesting thermal management because we can take also advantage of the heat from the radiation to be able to not only heat up the system, but also to be able to integrate these with, for example, residential applications to, for example, to heat up water. So, however, these solar redox flow cells, they are not commercialized yet. They have extremely low power and energy densities right now. However, our group was one of the main groups in Europe that somehow brought the sparkle again around this technology. You can see that the first work done on this one was in the 70s, but together with Aarhus University in Denmark, we filed a patent on this concept in 2015 because we noticed that some very innovative redox pairs were popping, and also higher performance of photoelectrodes would be able to ramp up again this type of technologies. So here in our group, we are mainly working on the device designs and also trying to upscale these to relevant scales. Of course, we aim to, of course, this becomes a solution that can penetrate into the market and present the theoretical advantages that we see. So just a short scheme about these type of systems. We have a photoelectrode here, in this case, a photoanode, where we have charge generation. Then we use in the redox mediator to be able to collect the charge and to deliver this into our electric load, and also to produce ions that will be exchanged through the ion conducting phase, and to be able to be combined with the redox species in the other electrode. We can also, and we have been working also on photocathodes. However, photoanodes, considering the electrode potentials, are more interesting in terms of performance right now. So this is a little bit what we have been doing in our group. From 2015, there was no continuous operation of this type of systems. The active area were also very, very small. So we carried out a project together with this university in Denmark, where we constructed some devices that were able to have a continuous operation. Active area was still an issue, and this is currently our focus, is to upscale the active area and bring this from a couple of square centimeters of active area to 25, and hopefully then to larger areas in the future, so we can be able to come up with scales that are industrially relevant. So we have also some very important works published in the literature. So the first all vanadium solar redox flow cell with a cadmium sulfide photoanode, and also now we are working on an hematite photoanode, which shows very stable performance. But then also as an alternative now, not talking again about solar redox flow cells, these are a very hot topic right now. In our group, we have a very close collaboration with a company based in Munich on these POMS redox flow cells. So these are very similar to the vanadium ones, but here, instead of the energy being stored in vanadium ions, we store them in POMS. POMS are a molecule, so a metal complex called polyoxometalates, that they display a lot of several oxidation states. So this means that per molecule, here we can exchange, at least in some cases, up to 32 electrons. So this means that we can store much more energy in these redox species when compared to vanadium, for example, that will enable to dramatically increase the energy density and also the power density, because the electron transfer with these redox species is very, very fast. Then another type of, this is more conceptual because you have different types already being studied, is the metal airflow batteries. So the metal air, this means that we have an electrode that is metal, but the other side of the battery is much more like a fuel cell. So we can, for example, using vanadium or aluminum or nickel, or also these POMs, we can use these POMs into one side of the battery. In the other side, for example, for transport application, this is very relevant. We can process oxygen from air and being able to discharge the electrolyte inside this battery. Then, due to the decoupling of power and capacity, this is why, again, redox flow batteries are so interesting. We can go to the station and just switch discharge electrolyte by charged electrolyte into a reverse reaction here, also in the case of the air side. So we are able to discharge where we need it, where we need the electricity, but we can charge the electrolyte in a centralized facility. So these are the projects that have been supporting our research on the field. And now I will briefly mention about what we are doing on hydrogen. So hydrogen, for a lot of people, companies, and institutions, is considered the fuel of the future, and hydrogen is being used today already as a utility, mainly in the field of petrochemistry, ammonia production, and also steel. But hydrogen is also seen as a very promising energy vector. Hydrogen systems are much less efficient than batteries in average. If we talk about electricity to chemicals and back to electricity conversion, but hydrogen are much more flexible than, for example, lithium ion batteries, because storing electricity in batteries is very, very promising in modern electrical grids and modern countries. But if we talk about electrifying or decarbonizing countries like China, India, or mainly in Africa and South America, the electricity grids cannot be so easily balanced with batteries. So in this case, hydrogen is a commodity that can be easily transported through very long distances, and despite the low efficiency, its flexibility is a critical advantage and can replace, in this case, for example, natural gas in the future, which is the commodity that is being commercialized in a global scale. So most of the hydrogen production today is based on the reforming of fossil fuels. In the future, we expect that water electrolysis will take a major share of hydrogen production, so the so-called green hydrogen. And within this green hydrogen, we have different technologies to be able to produce it. So we have alkaline electrolyzers, proton exchange membrane electrolyzers at low temperature. These are the more mature technologies, but we also have electrolyzers that work or operate at higher temperatures, in which the thermal integration here is very interesting because we can use less electricity to produce the same amount of hydrogen. However, I will skip this. So a fuel cell, I think most of you know, in a fuel cell, it's a galvanic device where we have our fuel, hydrogen, and we oxidize hydrogen, we produce protons, and the electrons follow through an external circuit and are able to produce electricity or to generate electricity. In the cathode side, we process oxygen, and the only product is water and some heat. So we have also different types of fuel cells. The type of fuel cell is mainly dependent on the type of electrolyte that we use, but this impacts directly on the operating temperature. So we have fuel cells that run at low temperature, again, alkaline fuel cells, PEM fuel cells, and also this phosphoric acid at intermediate temperatures. And we have also solid oxide fuel cells that work at the temperatures above 700 degrees C. So this impacts on the type of application where they have the biggest advantage. So typically, low temperature fuel cells more for transportation and portable power. Here, again, they are already being used in military applications where the decentralized and remote location is a very important requirement. But also these high temperature fuel cells will also have big application in terms of centralized electricity production. So these are some of the works that we have been doing. We produce some components for fuel cells. And here I was about to talk a little bit, one of our most disruptive works on this field, but I think I'm reaching already my time limit, so I will skip this. Just to mention that we are trying to come up with a new membrane that will allow us to fill a gap that no electrolyzer or fuel cell exists, which is between 300 and 400 degrees C. So typically low temperature fuel cells, they work under 200 degrees C, high temperature work at least at 600. So there is here a gap that we are trying to fill, and we are trying to come up with new membranes for this. And why this is important? Because most of the hydrogen that is consumed today is from the Haber-Bosch process, so the production of ammonia, that is an exothermic process, and they require large amounts of hydrogen. So here we have an industrial cluster in Portugal, and they would be willing to tomorrow get some hydrogen that is zero emission. And if we are able to come up with an electrolyzer to produce green hydrogen operating in the range of temperatures of the Haber-Bosch process, we can directly make heat integration, which is quite relevant in terms of industrial processes. This is a new class of electrolyzers that we are also studying. So these are ion exchange membrane electrolyzers. These are alkaline, but much more compact, like the acid counterparts. Typically the alkaline, these are less compact devices. So we are also making R&D. Only one company is developing this in Europe, which is Inaptor from Italy. And yeah, their advantages is that they do not use noble metals as catalysts, non-corrosive electrolytes, and their compact design. However, the level of maturity is still too low. So these are some of the projects that have been supporting our work on hydrogen. Thank you very much, and questions are more than welcome.
Tiago, thank you very much for a very interesting presentation of the different technologies, bringing us a new vision to the people that usually consider the battery as something that charges and discharges and does not look too much at the details and of the characteristics of these systems. But as Ricardo will show us, it is really important to look at that and have in consideration the specific characteristics of these devices. I believe in the end, we need this diversification of technologies to really enable the integration of energy storage in the system.
Thank you.
I would propose, considering the time, to leave the questions to the end, if you don't mind.
Okay.
And pass directly to Ricardo.
Okay, I will stop sharing.
Thank you. So Ricardo is a senior researcher, is a researcher at INESC TEC at the Center of Power and Energy, and has been working on the development of this energy storage optimization. And today we'll talk a bit on the work that we have been developing in several projects, and that we are also developing in Baterias 2030, together in collaboration also with the group of Tiago. So Ricardo, please.
Thank you, Clara. May I share my screen, please? So I don't think if you're seeing the presentation or the presenter view.
Is in presenter view, so.
Oh, okay. So I think this is it.
Yeah.
Yeah, okay, thank you. So I'll start my presentation with this question: why optimize energy management? And I think this is a tool that answers many of the challenges that Tiago talked about in the beginning of his presentation. So with energy management, we can reduce energy costs, we can increase grid stability, and enable further renewable sources penetration. And the main enablers for this are the widespread of smart meters, the increased robustness of forecasts, be it load forecasts, generation forecasts, market prices forecasts, and the widespread also of more and more flexible assets. We have stationary storage, we have electrical vehicles, and other controllable loads. So I will be focusing on two use cases where we have been implementing optimization. One is on a project that has already ended last year, and it was Flexergy, which was aimed to develop a predictive management algorithm for microgrids and hybrid parks. And the other is Baterias, that we have already mentioned today, which is an ongoing project aimed at establishing a renewable energy community in urban environments. So starting by Flexergy, in here we are considering that we have one promoter, and that promoter is responsible for a certain type of system, which is either a hybrid park or a microgrid. And he has in that system lots of technologies that can be controlled, with the main focus on the batteries. And we have come up with several optimization objectives that I will talk further on. But another feature that we wanted to have there is that the energy management should be applicable to different time frames. So we can do energy management for planning, either day ahead, either 1 year ahead for what is going to happen in the next year, or in the operational time frame. And this is not real-time operation, but it is what are the set points for the batteries, for the curtailable loads in the next 5 or 15 minutes. In the beginning, we had to consider different approaches. This is a list of the pros and cons that we found for each one of them. So in here we have mixed integral linear programming, nonlinear programming, and an agent of reinforcement learning. And I'd like to focus on the pros and cons that I'm showing here, because they support why we chose linear programming for our approach. So with linear programming, you have a guaranteed solution that is almost always the optimal solution because of the linearity of the equations. You have a limited number of model parameters, and those parameters can be easily obtained either through the manufacturer's sheets, for example, of the batteries, or through some conventional test procedures. And its application is independent of the system. You can use it in microgrids, in hybrid parks, where you have more or less battery assets, load assets. It's very flexible. So looking at the objectives that we defined for this use case, we started by defining the objective to minimize energy deviations. Now, this has the meaning when you think about forecasts. If you are providing a day-ahead schedule, you are going to be based on the forecast for the next day, which have an error. And when you are closer to delivery time, you have better forecasts. You know that what is that error that you committed in the previous day. So to minimize the deviations from what you offered in a day-ahead bid and the offer that you are now going to provide, you can use the objective of minimizing that deviation through the usage of flexible assets such as the batteries. You can also give a weight to the deviations across the day. So for example, for certain periods of time, a deviation can be more costly than on other periods. This can be a weight or a cost if it exists, a financial cost. We can always define an objective of increasing self-consumption. So what you have here, let me just pick my pointer. So what you have here is the balance between your generation and your consumption, for example, in a microgrid. And you have periods when you are injecting in the grid and periods where you are consuming from the grid. Now, if you consider that some periods have a higher cost than others, the energy has a higher cost than others in those periods, or that your feed-in tariffs can also be dynamic and you can receive more from injecting in the grid in certain periods, you want to shift the periods where you consume more to match with periods where you produce more. And that is manageable with flexible assets such as batteries. Arbitrage is just considering that you also can gain a profit from this by injecting in the grid. Now, I won't be getting into much detail for most of the assets that we modeled, just a quick overview that we could give set points for generation curtailment if it was needed. For example, if you have some constraints in the interconnection with the grid and you need to curtail your generation, we could provide that. We could also provide curtailment set points for curtailable loads. And here we considered that the loads did not have a rebound time. They were fully cut. It was a non-off set point. But it followed some constraints. It had a maximum downtime and a minimum down constraint, which said, okay, if I cut now my load, it can only remain cut for a certain period of time at maximum. And when it goes back up again, it needs to stay on for a certain amount of time also, and that is configurable. We also provide a set points for conventional generation for microgrids. But these are based on a band, so we were provided with an operational band and we provide a set point within that band, which could be 0. Now, this is where I would like most to focus this presentation, which is how we modeled battery energy storage systems and specifically lithium ion technologies. So usually in literature, when you're talking about linear programming, you use the bucket model. So the bucket model is a very simple model that is depicted here, where you have where the energy contents of the battery are included but are fixed. You also have a constant efficiency for charging and discharging, and no degradation is considered. So the aim of our work in this project in Flexergy was to come up with a model that could be tractable and yet linear. It could be described by analytical and explicit expressions. It was easily calibrated, and it's dependent on power, as opposed to models based on voltages and currents. And this is because within the battery, voltages and currents can have different values inside the battery itself. But their product, taking out the losses, is always constant. So we wanted to provide power set points. Now, all these 4 objectives here are met by the bucket model. But the first objective that must be able to capture the fundamental dynamics of charging and discharging and the impact of those actions on the energy content of the BESS, these are not met by the bucket model, or at least it's not a very accurate model. So we wanted to develop another one that would be more accurate. Now, to do so, many of the most complex models, but more accurate models, are the chemical models of the batteries that take into account how energy content is degraded over time because of the formation of some layers in the electrons. And all of that is not compatible with linear programming. But if we take some considerations about the lithium-ion battery, namely, for example, when the battery is at rest, the voltage is a good indication of the energy content. And when we say at rest, because we are considering an optimization step of 5 to 15 minutes, this is valid. This condition here is only for sub-second events that take place in the battery. So this is valid. Voltage is a good indication of the energy content. And when charging and discharging the battery, the voltage undergoes a jump drop proportional to the charging discharging current, as you can see here. What does this mean? That the higher the current that you are charging or discharging your battery, the energy content available shrinks, okay? You can charge less with higher currents and you can discharge less with higher discharge currents. Now, these are some of the simplifications. I will not go through the math here, but these are some of the simplifications that the model considers, that the model that you use considers. But the interesting part here is that many of the parameters, so what you can see here is that many variables are dependent, like the voltage for charging and discharging, are dependent on other variables, like the energy content and the current. But those we wanted to either model as parameters, constants, or as a linear approach to those variables. And many of those parameters were obtained with simple tests made on the laboratory. These are results from a battery used by FASEG, and these are the actual data that they provided us. And what you can see here is we were trying to come up with a voltage for charging and discharging. How do you do that? How do you manage to obtain a constant voltage for charging and discharging? Well, you would do a lot of charge and discharge full cycles at different C rates. For each one, you average the voltage that you are measuring during the cycle, which is each one of these points for charging and for discharging. There's two curves because there was two runs of the test. And then you average all the points for the charge and all the points for the discharging events, and you come up with a constant voltage for charging and discharging. This is a better approximation considering the open circuit voltage. That is what most works do. Now, the energy contents of the battery were modeled through a linear approximation. That because of the nominal voltage that you calculated earlier can now be expressed as a function of power and not current. The parameters of this line were obtained through a similar test procedure, where you charge and discharge completely your battery at different C rates and check what is the final energy fraction that is obtained. As you can see, for higher charge events, your energy fraction in the end is lesser. So you can charge less the battery with higher currents, like I said previously, and the same for discharge. So this shrinks. The same thing, very similar things can be applied when considering the efficiency of the battery. Now, this is very important because we can consider a constant efficiency for the battery itself, but not for the inverter. The inverter has a highly non-linear in the first half of the inverter, if you use smaller power fractions. So we wanted to come up with an approximation, at least for the first part, that was not constant. So we did a linearization of this part of the curve. Now, this is the complete BESS model with all these considerations. But you can see that it has the same points that the bucket model has, which are the limits for power charging and discharging, the update to the energy content, and the limits for the energy content itself. But now they are dynamic. We also wanted to take degradation into account. This is for planning, because for operation, daily degradation is very small, even if you have a very intensive use of the battery. But if you want to plan, for example, for 1 year, degradation will have a huge impact on the optimizations that you are making for the end of the year. So typically manufacturers give you this curve, and this curve, what it says is what is the total number of cycles that you can perform on a battery until end of life criterion is reached. This end of life criterion is usually for lithium ion batteries around 70 to 80% of their initial capacity. So when they are degraded 20 or 30%, that is the end of life criterion. And for different depths of discharge, you have a different number of cycles. Naturally, it is a decreasing number. So the more depth of discharge, the less cycles you can have. Now, we talk about depth of discharge because here we are considering that along the life cycle of a battery, what you charge is also what you discharge. So in here, you are not considering that the battery only degrades when it discharges, but you are aggregating the degradation from charging and discharging. So we do some transformations, and in the end, what we come up is with a line that tells us how much energy is degraded at each discharge event. And then we need another hyperparameter that we can put in our linear programming algorithm, where you say, okay, I have some notion that I want a certain lifetime for my battery, let's say 10 years. So we input that here, we know which is the maximum daily degradation, and we impose that as a restriction in our problem. So the battery can only degrade a certain amount per day. So that limits the number of charges and discharges. I will not explain this in fully, but we also were able to define reactive power set points, which, as you clearly know, is there's a relationship between active power and then reactive power that is not linear. And it's represented here by the PQ circle, that what we do is we segment that circle and approximate it by a series of piecewise linear approximations. And through a series of other restraints, we can impose also reactive power set points. If for some reason or for some times of day, which happens, for example, for hybrid parts, it's a use case for hybrid parts, you have to comply with a certain tangent of phi in certain times of the day. Now, I'm going to present some simulation results that we performed. Our tool was implemented in Python, and we used a very interesting dependency, which is pulp, that acts as an interface between Python and the solvers, where you can define your objective functions, your constraints, the models of your assets. And pulp comes with a very good default solver, which is the Coinor brancher and cat, which is not as good as a Gurobi or a Cplex, for those who know what I'm talking about, but it's very good and it's open source. For the simulations and for the operationalization, when we are scheduling the set points for the next 5 to 15 minutes, it's always good to use an MPC framework. So we have a sliding window, and when we are defining what are the set points for the next 15 minutes, we do an optimization for the next 24 hours, and we only keep the first step, and we impose that. And in the next step, after 15 minutes, we do another optimization of the next 24 hours, and so on, so on, so on. Why is this? Because you can always have newer and more accurate forecasts along the day. And also you can substitute the first time step of forecasts that you are using by measurements, and this reduces the error that you are committing. Now, this is a very complex graph, but I would like you all, to only focus on the yellow dots. So here is a 24-hour simulation with a 15-minute step where we performed the arbitrage. In a microgrid that had 2 batteries, 2 types of curtailable loads, and it is a typical day where we have more consumption than generation for that microgrid. And so what I like to highlight here is that with no limitation at the point of common coupling with the grid, the battery is charged when the prices, and you can see here that the energy prices are the red triangles, the prices are lower, and the battery is discharged when the prices are higher, which was something that we expected. Now, in the magnifying glass, I'm showing here the effect that considering dynamic SOC limits, dynamic energy content limits, has on the battery. So you can see here that for a higher charge current, this dashed green line shows that the energy content was reduced. Now, this is a very small reduction, or it seems so. And you could say, okay, but does that have an influence, an impact on the strategy? So we have performed some simulations and checked out that yes, it does have an impact on the, it's not very great. You can see that the full bars along with the empty bar, the dust bars, they are pretty much overlapped, but you can see there's a difference because of those dynamic shock limits. Now, when you introduce a limitation in the point of coupling, you start to use the other types of flexibility that we introduce them with a cost associated. So, for example, to curtail load or to start the diesel generator, we introduce the cost to them. And so they are not used when there's no limitation, but when there is, you can use them. And what you see here is that in these in these bars that are not filled, you can see the minimum uptime and maximum downtime condition that is applied here. That was 1 hour. Now, this is another example, but not using load curtailment, but conventional generation. And you can see these like blue bars that come up here, and that are you start to use the generation. The prices are also always higher. This is an example for a hybrid park. And here what we wanted was a compliance with a red schedule. And in the end, this day was very good because it had 0 total deviation. And here we are also highlighting the set points of reactive power. Now, this may be more interesting. We performed the simulation for a microgrid for over a year, and we wanted to see what was the impact of considering degradation, that daily limit to the degradation, on the objective function value. In this case, we are performing arbitrage, and on the degradation. For minimization of energy deviations, the difference was not very big. Because we did introduce a difference between, they had forecasts and our had forecasts that was in par with literature, with the state-of-the-art literature, and the usage of the battery is so it's not so intensive. So the values obtained either for the objective function and the degradation are very similar. But when you consider another objective function that is more intensive for battery usage, like arbitrage, you see a difference. And what is that difference? When you use an unconstrained strategy where you do not consider a limit for daily degradation, the objective function value was better by 27%. So here it is negative because it was a profit. But on the other hand, degradation increased by 19%. So there is a huge impact on the strategy, and there is a huge impact on our objective function value and the degradation. So for long-term analysis, you need to consider that hyperparameter that is the lifetime, which we consider 10 years. You need to adapt it to your needs. As for the computational burden, I only want to highlight here that we performed several cases where we use different optimization horizons, different the granularity of our data. And for each one of them, even for the most complex, where we had to optimize 288 time steps, they were always below the minimum granularity that we are considering for using operational optimization of energy management, which is 5 minutes, which is 300 seconds. So here we see that in the worst case, we only took 110 seconds. So our tool was able to be used for operation. Now, this tool was implemented on live. It was showcased in a live testing in the Democrat testbed of FASEC, where they had these assets. And it was integrated in the software that they've developed called ES Manager, that includes a human-machine interface, some forecasting models, and of course, our tool that was provided as an API. Now, very quickly, I'd like to talk also about Baterias 2030, which aim to implement a community, an energy community. And in this case, the main difference is that we have several promoters, and each one of them has their own interest in mind, okay? But a certain degree of orchestration is nonetheless needed so that all can benefit as a whole. Now, how do we tackle this? Our approach considers two stages. One stage where we optimize each promoter individually, each member of the community individually with its own assets. And then we do a second stage where we do a community optimization. But how do we guarantee that individual interests are taken into account? By introducing a restriction on the second stage that says, okay, your new cost found in the second stage of optimization cannot be worse than the one found in the previous one. And by defining that, we also include in the objective function of each individual member the possibility to trade energy in an internal market that needs to be linked to a cost. I'm not getting to details on how this cost is found, but it's always better for someone to trade within the community than to trade with a retailer. Some formulation here.
I would suggest to pass to.
Yeah. Some results were shown there, but this will be live tests in Braga, in municipality, and I'm done. Sorry for overlapping the time. Thank you, and Q&A time.
Thank you, Ricardo. Thank you, Tiago. So I would ask you for 2 more minutes, so just to have the opportunity also to ask you the questions on the Q&A. So in the Q&A there are 2 questions to Tiago. The first one is related with the solar redox flow batteries. And you meant the solar fuels, and so Justino is asking which kind of fuels are we talking about?
Okay, so very quickly. So regarding redox flow batteries, let's put me here. We should also address the issue about redox flow cells, because when we are using redox flow batteries, of course, we are storing sunlight into liquid electrolytes. This is what we get with vanadium, with the POMs, and also with these organic ones. When I mean, in this case, solar fuels is more about solar redox flow cells. So these are, for example, you have a field with photovoltaics, for example, but then you have a electrolyzer, which is an electrochemical cell that takes energy and produces fuels. And in this case, the most typical one, hydrogen. So photoelectrochemical water splitting. Then we can also produce methane, propane, and the most interesting ones are the liquid ones at the conditions of temperature and pressure. So ammonia and methanol. So we are using these in these cells. In the other electrode, we take CO2, anthropogenic CO2. We feed it with water and sunlight, and we are able to produce a panoply or a different portfolio of fuels.
Thank you. The other question from Pedro is to ask you which technology you consider most promising for seasonal storage, and particularly for the Portuguese case.
Okay, not a simple answer to this, but what I think will be the answer to here is moving away from centralized production to decentralized production. Of course, at decentralized, you have a panoply of technologies, batteries integrated with artificial intelligence models that you as a consumer, you are also be able to be a producer and to feed electricity back into the grid. But to be able to become this a global market, you need some vectors like hydrogen, or more interesting ones like hydrogen vectors like ammonia or methanol that you can ship any place in the world and be able to decarbonize or defossilize, putting the energy less fossil, let's say.
Yeah, in the end, this for the seasonal issue, the besides water, that today is really an issue, the hydrogen and the other.
Well, I did not mention, Clara, but we have a radical project that I'm leading in our group, which is catalytic methane decomposition to produce hydrogen, clean hydrogen from natural gas. It's very interesting because if you use biomethane, you can have a circle with CO2 like doing with the nature does. You take CO2 and you transform it into fuel in a clean way. So this is a different type of solutions that, apart from electrification, that we are also aiming at.
Tiago, thank you very much. I will just ask and to finalize to Ricardo. So in the end, you propose this approach for the degradation that, as we have seen, does not affect too much the result on the scheduling of the battery. But I know that you have tested some other strategies, and there is a balance between what we can do. Can you talk to us a bit more on that?
Yes, I think the main question here in this approach is the definition of that hyperparameter, that is the lifetime. So if someone was to define that, it would really need to have a strong economical preview of what would happen in the future. What would be the prices? What would be if the promoter was going to increase the generation in that microgrid, or if it is previewing an increase in load? So it depends on several factors. The objective function, it depends on it's really an approach that it's not it's so easily explained and should be considered with much care.
Yeah, but in the end, it shows that it's also necessary on the optimization to really work on these more detailed models without entering in the very complete models of the battery, because in fact it has an impact on the scheduling of the battery. And so we hope that future work can bring this modeling to other technologies, such as the one that Tiago presented. This is also one of the objectives of our group, and also in collaboration with you. And we hope that in the end of Baterias 2030, we have some more real results to show by both groups.
We are also in Baterias 2030, yeah.
Yes. So I would like to thank you again, especially Ricardo and mostly Tiago, for bringing us very simply, very clearly the explanation of these new technologies, and also to the ones that are here listening to us and that stayed a bit more longer to close and to participate in the Q&A. Thank you very much.
Thank you.
Thank you.
Bye.
Bye.
Bye.